So let me first perhaps talk a bit about data science and the role of the data scientist as the job of the future. In Eindhoven I'm also head of the Data Science Center Eindhoven, which is a very large initiative because we see that just as computer science emerged from mathematics, we see that now something spectacular is happening just because of the availability of data. There is a new type of profession that in my prediction will be as large as computer science is now. Because just there will be much more data and there will be people that have these profiles being able to analyze that data. So what are the 4 typical data science questions that people can ask? These are very generic questions and later we will look at that in the context of processes. What has happened? Why did it happen? What will happen? And what is the best that can happen? And these are the 4 typical questions. The first 2 are about the past, understanding what has happened in the past. This is predicting what is going to happen, and this is how to make it happen. And so if you're in the area of predictive analytics, then these are the things that you look at. If you are interested in process redesign, then you look at these types of things. So how could I do things better? Let's take 2 examples at a completely different levels. So the first level is at the level of a hospital workflow, where you are treating patients, and these processes can have all kinds of problems. There can be problems related to waiting times, the fact that some people have to work very hard, other people have nothing to do. There may be deviations. So for example, in the Isla hospital, where we are now currently doing an analysis, we are looking at what is the relationship between people deviating from the expected workflow, and what kind of impact does that have in terms of cost and incidence. And then you see that the costs increase spectacular if people start deviating, because all kinds of tests are done for nothing. So this is at the level of a hospital workflow, and you can ask these questions. So what has happened? Did we manage to treat or to help the patient within a certain time frame? If we were not able to treat patients within a certain number of weeks, then you would like to ask yourself, why is that the case? You would also like to ask yourself the case, like if we are now treating a patient, will we be able to treat that patient in time? That's another example. And you could think of redesign and better control to make that happen. So very general questions. We can also look in a hospital at something at a completely different level. So here you can see me standing in front of an X-ray machine. We have been analyzing for many years the data from such machines. If you look at a machine like this, you would like to know, that's how the collaboration with Philips started. They need to prove that they are testing the machines in the way that they are actually being used in the field. So they need to gather evidence how these machines are being used in the field to have realistic tests. So that was the first thing that we did with Philips. After that we started looking at other questions like why do these machines sometimes malfunction, under what conditions. If the machine is broken and an engineer goes to the hospital, the engineer has no clue what he will find. But at the same time all this event data is available. So we have developed techniques to extract so-called signatures that will tell you what is the typical behavior if a particular component is broken versus the rest of the behavior. So you can automatically learn a signature, and then kind of if a machine is broken, the engineer will already take the component with him that is most probably broken. Can we predict that the particular machine will break down, etc., etc. So you have all kinds of, again, data science questions, but now at the level of hardware. And all the levels in between you will find such questions. So in this lecture I will make the point, for the people in the lab it's quite obvious, but for people outside the lab it's perhaps not that obvious, that in the end it's very important to look at the process. Data mining problems typically look at one particular activity, one particular element of something which is much bigger. In the context of process mining, we always look at end-to-end processes, because you would like to improve the process, you would not like to improve the data. That's not the goal. So here you can see examples of process-centric questions at the level of hospital workflows and at the level of these X-ray machines. I see that the beamer has some problems. When I look on my computer, this will look completely different. So that is the setting. So in the Data Science Center in Eindhoven, you have 28 research groups focusing on questions related to data science. Also things like basic statistics, but also things like ethical issues and privacy issues, which are very important, of course. Then if we zoom into process mining, it's connecting model-based analysis and the data-oriented analysis. So typical data mining techniques are at the bottom. Typical things that you find in the area of formal methods and in the area of business process management, workflow management, typically at the top. Things also like business process simulation, it's also something that is at the top. Typically you're analyzing a model, you're not analyzing the data. Here, people that are at the bottom, they analyze the data, but they are not necessarily analyzing the process. Typically just an element in the bigger process. So this is one way to put it. Another way to put it is the fact that we try to answer performance-oriented questions and compliance-oriented questions. So performance-oriented questions are things like where are the bottlenecks? Why are they there? How can we remove them? Why is the utilization so different in different weeks of the year, etc., etc. Here we look at deviations. There is a kind of normative process how things should be executed. And we look at situations where people deviate and try to understand it. So here it can be that two activities are executed in the wrong order. But here you also have questions like, for example, function separation. That means that it is not allowed that the same person executes two activities, like an execution activity and a check activity. That's also an example of a compliance question, which you need to look at the process to understand what it means. And you cannot see that if you look at a single activity. So this is one way to position it. This is another way to position it. Here you have this picture that I showed you before of the typical data science disciplines. And this is like the bridge to more process-oriented disciplines. Okay. So this is the broader setting. Let's now take a more detailed look at the topic of process mining. As I said, this talk is intended to be very introductory, to just give you an idea of what it is. Later I will tell more in detail about alignments, then it will get a bit more technical. So let's first take a look at the typical way in which we use models. The typical way in which we classically use models is that we start by making a model by hand, and then we generate behavior from it. Yeah? So we make a simulation model, we make a specification of code, or we make code, or we configure an ERP system like SAP or Oracle. We start from a model, and then behavior is generated from it. Process mining is of course related to these two other things, where you go in the reverse direction. Let's try to make it a bit more visual. So if we look at play out, we start from a model. This is not process mining, this is the classical way in which people use process models. You have a model, you configure a system based on it, or you generate a system based on it, and then you get behavior. For example, here you see a process model in terms of a so-called BPMN model. So who in the room is familiar with BPMN? So that's why it's good that I didn't choose a very advanced topic. So in this notation what you see is all the cases start here and they are processed according to this procedure, and ideally in the end they end up here. So what do you do? It always starts with a registration step. Then after a registration step, we do two things in parallel or in any order. We always check the budget, D, and we do one of these two activities here. And we need to make a choice. This is AND, this is an XOR. So we either do this or we do that. Then if we have done one of these two and we have done this one, then we can make a decision. If we make a decision, we accept, we reject, or we reinitiate the request. Yes, you have loops, you have concurrency with this AND split and this AND join. You have choice with this XOR split and this XOR join. Of course, you also have sequencing. Is the picture clear now, what it means? So if we now handle one case, one request according to this process, then the following may happen. So suppose that we put this into an SAP or an Oracle system. Then we start by executing the first activity. And this activity is of course executed for a particular request. So you have something like what we call a case. And concurrently there may be thousands of cases running here in parallel, but I only show you one. So you have for a particular case, this activity was being executed at that point in time by this person. Then we have first, so this is a join, so we don't have to look at it. Then we have an AND split, so we do D, and we choose one of these two. In this case, it was decided that B should happen, so now we execute B. It was executed by Mary at a particular point in time. Then we check the budget. This was done by John again. Then we make a decision, and the decision is to accept the request. And so this is one audit trail, one execution of this process. So if you're doing simulation, if you're doing system configuration, this is what you do. Okay? But of course, this is just one example. If you look at a particular process model, you could also follow this path. So now it started with the D, then we did the C. We make the decision says we need to go back into the process. So we go through this loop. Now we do B rather than C. Now we do D. We make the decision, and the decision is to reject the request. So this process model has an infinite number of possible traces. So we have seen these two. There are these candidates, but there are infinitely many. Because of the loop, we can go as many times through the loop as you want. So this is typical play-out behavior, generating behavior from the model. Process mining starts from the behavior rather than models, because models always lie. They are never reflecting what is really happening unless you enforce them in the system, but people can do no other way, but then analysis is not very interesting anymore. Okay. So let's take a look at the reverse play-in. Play-in, you start from behavior and you automatically construct a model. So you can think of this as that you make visible what are the traces that people really follow. And so this is perhaps what people have modeled, and we would never see that people cycle like this, but you can think of this trace here as a kind of event log showing that many people have cycled along this path. Okay? So this is process discovery making this visible. So in terms of the traces that I showed you before, if we have these example behaviors, then what we see is we always do B and D. If you look at all the examples, there's always B and D. And it ends with G or H. E is always kind of the third activity, A is always the first activity, etc., etc. So I think everybody will agree that this is the process model describing these examples, right? This model has four possible executions, and we do not see anything else than these four possibilities that this model allows. So here it's very, very clear. If you have a situation like this, it may become more tricky, but most discovery algorithms, based on this soup of behavior, will construct this process model. just by looking at particular patterns and putting them in a model. Yeah? That's the basic idea. The difficulty in this process is always if processes are concurrent, as you see here, because then, let's say, all the classical techniques fail, they do not work. Yeah. You can do these things without any modeling, so you just start from event data and you automatically get a model. So you can go to a hospital, you can extract the databases, you have to make sure that you extract data where every event then refers to a patient, and that you have something like a timestamp, but the rest, that's all there. So you can automatically construct a model. So here is an example of a smaller process and a smaller data set. There are 208 cases, 6,000 events. And here you can see the events, and this is it is in Dutch, but it's not very important. You just see a CSV file. The first column refers to a house or an apartment. This is something that, so this is from a company called Vestia. They rent houses to people. And these are all the events that happen with respect to a house or an apartment when somebody says that he wants to cancel renting the apartment until somebody else rents the apartment. So I think you have approximately 80 different activities here. So for example, there are activities like that you should update the rental price. There are activities related to all kinds of checks. So are there new problems in the house, etc., etc. So there are all kinds of activities related to that. You cannot, if you stop renting, you cannot just leave the house. If you completely destroyed it, you need to repair things, there are inspections, or you need to pay a fine. If people have changed things, you need to change the map of the apartment, etc. So you see these things, and of course you have a timestamp. Based on that you can construct, I hope it will work out. So here you see a process model. If I zoom into this, then you can see a particular sequential part of this process which was executed 34 times. Yeah. Note that this was all done based on a simple CSV file. I knew nothing about the process, and now I suddenly know, oh, in this process there's apparently this sequential part that was followed by 34 cases. Yeah? So this is a simple process. This is a more complicated process that I often use to illustrate the variety of behavior in some domains. This is a group of patients treated in the same department in a Dutch hospital in Amsterdam. They all have more or less the same problem. You can see that we look at 627 patients generating this amount of events. Here you see a particular audit trail of a patient, so you can see that we know much more information than what I was showing in these abstract examples. So we know not just the timestamp, we do not know just the name of the activity, we do not know just the identity of the patient, but for example we know the age of the patient, the color of the eyes, what kind of insurance that they have, etc. etc. So we can take this data and automatically construct a process model, and it looks like this. Yeah? So this is a homogeneous group of patients. Yeah, so people that want to design systems or that want to do management jobs, they should first understand where this complexity comes from before thinking that it can be done much better or much simpler or much cheaper or whatever. Yes, I'm sorry that so this is a connected graph. So this is a social network showing how work is flowing from one department to another department using this additional information that is there. So this looks like a problem that you have maps like this, and for practical applications it is also a problem because life is complicated on the other hand. You can, however, make it as simple as you want. It's the same as if I would show you the map of Moscow and I would draw every street using the same color and the same way. It would be much more complicated than this. But still you can understand the map of Moscow because you zoom into the parts that you're interested in, or you leave out things that are insignificant. Or if you take the metro, you will look at a different map than if you take the car. You need to make these maps context dependent to make them most useful. I'll come back to that later. So that was discovery, play in based on data. Now the most important thing, and later I will talk about more technical things related to alignment, that is related to this. So this is the most important thing of process mining. It's the fact that you can relate real behavior, reality, things that have really happened, to a model. That sounds very simple, but it is not. And if you look how people use models in practice today, there's often there is the database with data, there are pictures that people make, and they are completely unconnected. And so replay connects these two things. So this is to avoid situations like this. So this is the design of a very safe system, to avoid that people are going in. But if you do conformance checking, you will see, well, there are some deviations from the expected behavior. So in this case, we have a model, that is this model, and we have reality, and we confront these two with respect to each other. Yeah? So how can you find out these things? You find out these things by simply replaying reality on top of the model. So I don't know if Yandex is showing here where the traffic jams are, then what it is basically doing, it is replaying the current traffic that it knows from the devices that are running around, and it is simply projecting it on the map. Yeah? You can do a similar thing when it comes to process behavior. These are the things that have really happened, and we project that onto the model. So in this case, it is extremely boring, because here we have a trace that fits into the model. And so we can now do a C, that is possible, and we now need to do a D. Nothing is going wrong. We do an E, we do a G, and we reach the end. Yeah, so reality and the model agree completely. Let's now take a look at this scenario, and if you by now can read these models, then you will see that in this trace the budget was not checked. Whereas the process model, remember this was an AND, the process model says that you should always check the budget before making a decision. Let's now just try to replay it. So we register the travel request, we get a detailed motivation letter, and now in reality, somebody made a decision. So this is what has happened. But according to the process model, you cannot make a decision if the budget was not checked. So using replay, you can detect this problem. We just move on replaying, and in the rest of this trace there are no other problems that we encounter. So we see that there is a deviation, and we can analyze it. And so we can, for example, if this frequently happens, then we can look at which is the person that typically makes the decision without the budget being checked. And you could drill down using standard data mining. So here you have an example from reality. In this example, if I zoom in, there you have an activity, this one, which was executed 23 times, but it was not supposed to happen. So I will not expand on the example, but this is a re-evaluation of something that should not happen, but it did happen. Here you see that 11 times this happened while it was not supposed to happen, and there were 2 times where this should have happened, but it did not happen. So you can see deviations between model and reality. So that's conformance. And please remember the initial model that I showed you at the very beginning. Why do we do process model? Why do we do process mining? We would like to find out compliance-related questions. Why do people deviate? I think the previous example kind of illustrates. We also do it because we want to make processes better and understand why there are high costs, why there are delays, why are resources not used in an optimal way, etc., etc. To do that, you replay the log, but now with timestamps, which were used to discover the process in the first place. So I can simply do the same thing as I did before. I replay the log on top of this model, and then I reach the end. And what I've done is I recorded all the times that I executed these activities. So I know exactly how much time was being spent in between all these activities. So I know, for example, that there was 20 minutes between registering the travel request and checking the budget. So if I do this for one case, unless we are in the area of project planning, it's not that interesting. However, if we are in a hospital and we have thousands of patients, it is interesting to see where do these thousands of patients, where do they get stuck, where do they lose time. And you could try to analyze them. So we can do that at a larger scale, and then you get frequencies of paths and activities, you get durations of activities and waiting times in between activities, and you get the type of information that you would like to have. Note that you can do that without modeling. You just take the data, you extract the data, you get a process model, you replay a reality on top of that process model, and you get indications where are the bottlenecks, why are they there, etc. Yeah? Everything clear? Let's now go a bit deeper, sorry for the typo. I'm going to tell now more about this notion of alignment, and now I will make it a bit more technical. So what we saw before in this example, remember that this was the example where D did not happen, the check was not done in reality, whereas the model said it should be done. We can analyze that very precisely using the notion of alignment. So the top row corresponds to a trace of something that has happened in reality. The bottom row corresponds to a path through this of this process model from beginning to end. Yeah? If I take a look at this trace, I cannot find the path to the model that is exactly A, C, E, G. But I can find this path, and that is the path where there is one part where they don't agree. This thing that you see here is a so-called move on model. So the model needs to make a move of something that didn't happen in reality. Yeah? So this is the plus and minus symbol earlier, this is the kind of diagnostics that you see now here, but now at a more precise level. Let's take a look at another trace. So here, something should have happened in reality according to the model, but it did not. Here, this is a trace where we see that there is a G and an H, so something too much has happened here. Something that was not allowed according to the model did happen. Let's replay it. So we do the A, we do the C, no problem. And now we have this H that you see here, but H is not enabled yet because we didn't make a decision yet. Also, if we look a bit forward, we will see that there is a G here, so later there is another decision. So we decide to ignore this H, say this was not possible, and just continue replay. And if we do that, we don't see any other problems. Yeah? Do we understand this? Let's now put this in the context of alignments. So I showed you now a path through the model that was different from the path that we had seen in reality. And the only difference was with respect to H. So this is the corresponding alignment. And note that this is different than before, because now something in reality has happened which was not possible according to the model. And again, I cannot find a path with less than one difference. Okay? So that's what we're looking for. What is the closest path through my model? Now as a human you already get into trouble if you do this. So this is a trace of something that we have seen in reality. So what is now the corresponding model, what is now the corresponding path through this model? It doesn't exist. But we can try to compute the path which is closest to the behavior that we have seen. And then, for example, you get a path like this. So what do we see here? If we create here the alignment, you can see that it started A, C, E. So what you can clearly see is that the D is missing here. Yeah, so we have a check is missing, so-called move on model. Here we see two move on logs, things that happened in reality, which could not be replayed in the model. So we have these two things. So here we have two D's following one another. That's clearly not possible according to the model. Here we have a B and a C. And clearly, yeah, we cannot do both, because this is an XOR split. Yeah, so we can see this. Note that there can be multiple alignments. Now I choose to do this. I could also have swapped that. So that's why in our tools, we sometimes compute all alignments having the lowest cost and then give equal probabilities to them, or weighted probabilities. Yeah, that's how we can do it. So I hope that you can see that this is an optimization problem. And if you look at the complexity of this problem, it is terrible. So you need to be very smart to solve this problem efficiently. So we are using these types of techniques also in the context of genetic process discovery, where we use genetic mining to just basically guess models. We take parts of one model, take parts of another model and combine it. And each time we need to check the quality of that model with respect to the whole log. So for every trace, we need to solve an optimization problem. So if you now have a genetic approach and you have a population of 1,000 models in every generation, you have a log of 1,000 traces. That means that you need to solve 1,000,000 optimization problems just to go one step further in the net. So that is why it is very important to do this this as efficient as possible. And there are of course much more efficient discovery techniques, but it just shows you that we did a lot of work to try to get this as efficient as possible. Yeah, so let's, as I said, I'm going to get slightly more technical. So what you see here is a Petri net. And this Petri net models the following behavior. We start here, then we can add items, then there is a token here. We can then add as many items as we want, again and again. We can then finalize the order or cancel the order. If we cancel the order, we are done. If we finalize the order, then there may be a delivery, but there may also be this action. And this action is black, it means that it cannot be seen by the environment. It's some kind of internal action that is not exposed. Somewhere in the system it is happening. And so the environment cannot not see that. So what you see here is that we have two transitions with the same label. It's already a complication of what I had before. Besides that, I'm using Petri nets now. You also have these invisible transitions. And for the people that are not familiar with this area, if you do real life things, you have lots of duplicate transitions. That the same thing basically can happen at multiple places in your process. Or you have these silent activities to model simply the logic. So for example, if you have something like an OR join, that you can do A or B or A and B, then you need to have transitions of this kind to model all these decisions. Okay? So you get lots of internal behavior. Suppose now that this happened in reality, add items, finalize, finalize, clearly something that doesn't fit. So the question is now, how can you compute an alignment? And so how do you do it? Because I said it's an optimization problem, and I'm now going to show you how. So if you look at this example and this trace, these are two possible alignments. note that now you have 3 rows, and that is because I have an add items T1 and I have an add items T2. And we also have this situation, let me point to the right thing, added order here, T4, that's a black transition, so we need to have more information. So if you look, if you see this action here, added order, it's an internal move which you cannot see from the outside. Yeah, so this is clearly not a problem. This, however, is a problem. Or if we take a look at this one, this is also a problem. And so here a delivery is happening in the model, which did not happen in reality. Here a finalization is happening in reality, which is not happening in the model. So these are the 2 explanations that you can take. That have, and so here we have this problem, here we have this problem. That is what I just said. So how do we analyze this? We take this process model and we can also model this trace as a sequential process. Right? This battery net just models this trace. This is the process model that we started with. And now we can take something like the synchronous product of what we have seen in reality and what was in the model. And then this observed behavior, this model behavior, but from now on we can just talk about process models. We now take the synchronous product. Let me make it a bit bigger to explain to you. So the top row is the observed behavior. Yeah, so we saw add items, finalize, finalize. The bottom part shows you the original model. So what now happens ideally is that reality and model take the same move. Yeah, so if add items happens here and add items happens here, and they happen at the same time, that is effectively the same as this transition. If, for example, if we take a look at, for example, at finalize, and we look at finalize here, and this transition and this transition, if I put them on top of each other, I get the green one. Yeah, do we see this? So the actions that are here in yellow mean that in reality something is happening which is not mimicked by the model. If you look at the purple ones, they correspond, something is happening in the model, but it's not happening in reality. And the green ones are the good guys, because that means that model and log do exactly the same thing. Okay? But this allows for all the behavior. I should make a special comment on this gray task. So this was an activity in the model, which was a silent activity, something that happened but that we could not see. So we should not give a penalty for that this is happening. Do we understand this? So I take just some kind of product of these 2 behaviors. Now I can just construct a so-called reachability graph, the automaton or the transition system or whatever term you prefer, based on this model. And so I can just compute the behavior that I've modeled here, and then you get something that looks like this. Yeah, so always it explodes, and I'm using the coloring that I had here. Yeah, so this is my initial state. At the bottom I can see my desired final state. And all of these circles that you see here corresponds to states of both the net modeling the environment and the net modeling the model itself. Okay? I get a reachability graph, and now, so I come from Eindhoven, so we are fond of shortest path algorithms that were invented there. So now it's basically finding a shortest path from the initial state to the final state gives me an optimal alignment. And the one with the lowest number of moves. So I assign cost to desirable moves, and then we have a shortest path, as I just said. So here you can see it. What I've done now is I've assigned cost 1 to all moves on log, and all moves on model, the purple ones. The green ones have cost 0, and the gray ones also have cost 0. And then you get this, and then you can see this, we start with cost 1, and then if we use the shortest path algorithm, we will see that to reach the final state, we always need to have at least cost 1. Yeah? So that's the way that it works. So here you see a shortest path, but there are multiple, as we have seen before. It's highlighted, so here we make a synchronous move A, synchronous move, we go down, etc. And finally, in this last state, we need to do, so here was still cost 0, but here we can only do bad things. So we get cost 1. So this is the alignment that corresponds to it.
And there is at least one more shortest path, right?
There is one shortest path more. So if I go back. So I just showed you this one, I think, but this one is also there. But that involves executing this great transition.
But it will still have the cost 1.
It will still have cost 1. Yeah. Because I assigned cost 0 to that silent transition. There is in fact a technicality that we'll get back to in a minute. Yeah, so we find here the shortest path as I just showed you, so we get an alignment. So this is the alignment that I've seen, but as indicated there is also another one. The technicality that I here have to do is we would of course like to avoid paths of cost 0 in a cycle. That is a technical thing. So for these silent activities we assign cost epsilon, but it doesn't influence the result because at the end we can simply subtract these epsilons again. So it's just to make sure that we do not get stuck in an infinite path which is still optimal. That's a thing that we do. But I hope that you can see that this is a horrible problem. So we already have a model with infinitely many states, possibly, or at least an exponential number of states if there is concurrency, but if it's unbounded, there are infinitely many paths. We have a trace, and then we can do everything in the model that we could do, we do everything in the trace that we could do before, and we can take the product. So this is horrible, so we need to be very smart. But luckily we have a background in PetriNet, so we can solve this. And the way that we solve this is we are using an A-star algorithm, which basically avoids exploring this. So our search space is infinite, potentially, but we just avoid starting to look in paths which will never be promising. Yeah? And how can we do that? We use a so-called marking equation, and the marking equation helps us to rule out all paths from which we can no longer reach the final marking. So we can have a linear algebraic representation of what are necessary but not sufficient conditions to reach the final state. Then we can use that using an A-star algorithm in two ways. So we can use it in this way. So we don't explore paths which do not lead to the final state. And so a model may have deadlocks and all kinds of problems. We avoid going into these paths where you can no longer reach the final state. Moreover, we are, so for A-star, a good underestimate is very important. And we are using this marking equation to produce a much better underestimate, because we can give a linear algebraic representation of the paths going to the final state, and to compute the cost we do not need to know the order. We just need to know how many moves of what type there are, and you get that. And so this is a way to do it very efficient. And so if we're using these genetic mining algorithms, we can do it, so we can do many of these checks per second. Of course, it's still exponential in the number of different activities, so if you have very big models, it's still very challenging. So we are also using all kinds of distributed mining algorithms to do this in a distributed way. So I hope that I convince you that alignments are very interesting and also essential. They are there to diagnose deviations and to squeeze behavior into a model, even if it doesn't fit in the model, because that is important for doing, for example, performance analysis. You need to squeeze reality into the model, even if it doesn't fit. So here you can see some screenshots of tools that we have developed to do such type of analysis. So this is conformance. Here you see two activities which were almost always skipped. Yeah, so we see something like this. The yellow circles that you see here, if we click on them, we see all the activities that have happened in this state that were not supposed to happen. So we see exactly this alignment-based information. We can also simply inspect the alignment. So what you here see is a visualization of exactly the alignments that I had before. So if they are green, that means that model and log agree. If they have a different color, then it's a move on model or a move on log. Yeah, so we can do this for conformance checking. Once we have these alignments, we can always replay reality on top of the model, even if it doesn't fit perfectly. And we get, so here it's clear that here is a bottleneck and here is a bottleneck. And we get that by replaying and looking at the timestamp. And so this is, if you're interested in improving these processes. Something about tool support. For that I do something dangerous. Let me just show you one plugin in Prom. So so now I'm loading the event log, and I hope that you remember of this housing agency. Simple 3 columns, etc., etc. I load it into Prom. So if we now look at it, we can see that indeed there are 208 cases, there are 6,000 events. It's just what I said to you before. And now I can apply a plugin to this. So I'm now taking the raw data that I got from this housing agency. I use a discovery tool on this, and what I will see, I hope, is that so now it created the data structure. So what you see is, if you have very good eyes, is that there is a process model, but it is very big. This is the map of Moscow. If you would show everything using the same color and everything the same. Yeah? So this is a huge model, but I can make it simpler if I want. So I can move it down. So now you still don't. I see lots of things, but you don't see that much. So what you see is that you can see the model. You can also see numbers. I can go further down, and it gets simpler and simpler. So what I can do is that I can make it very simple. So now we just have a few activities. So this is the same as if you're using an electronic map. You can zoom in, you can zoom out, you can look at parts that are interesting for you, etc., etc. What is important to see, so you see the yellow tokens floating on the screen. So what it has been doing in the background, first it discovered the process model, using the so-called inductive mining technique. Then after discovering the model, of course the model leaves out all kinds of things. Then it created the alignments for all of these traces. And then for the first 50 traces, it is doing the replay and visualizing this. So these are not all the traces, but it always takes the first 50. You can also save an animation that will show you everything. What is important, if you look at these tokens, they correspond to real houses. So this is real data, this is not simulated data. So if I move it up a bit, that the model is slightly bigger. So again, and you can see that, yeah, it's again recomputing the alignments, etc., etc. So this is, I'm now filtering based on the number of activities. I can also filter on the paths. So if I move this slider down, what you see is that the path gets more sequential. So I can filter both on activities based on their frequency, but I'm now filtering on the paths. So if I move this down, then I see a sequential process. As I see a purely sequential process, which is the most frequent trace that we see. So we can, we can play with this and then look at all these things. So what you can also see, but I will not highlight that. You can, for example, take a look at the alignments themselves. These are things that you see here. What I can also do, if I would prefer to see a PetriNet model of this, I can go here and I can view a PetriNet of exactly the same behavior that we had before. So I can convert it to the notation that I have. So now I cheated, now I show two plugins. But it gives you an idea of what kind of functionality is provided. And this is one of over 600 plugins. So Prom looks like this. I showed you now one of these things. Most of the other ones do not look as nice as this one, I should admit. But it's just to show that there is a whole area of analysis techniques that you can apply in these things. And so, for example, there are plugins, if you have a decision in your process, to understand what are the factors influencing that decision. Do, I don't know, male patients go left, female patients go right? Or do patients that were very delayed in the beginning go left or right, etc. So you can ask all these data mining-like questions in the process context. There are also commercial tools. So this gives an overview of some commercial tools that are basically based on the ideas that we have developed in the context of Prom. And these two that you can see at the top, they are started by here. These are two of my best PhD students that started a company on this. And this is a student that worked on this Prom mining framework and then started another company based. So here, yeah, the resolution is not helping, but also in Disco you have like a slider. I don't show the tool, but here you see all the activities. Here I just see the two most frequent ones. You can see that on average there is 56 days between these two activities. And this is something in the middle, but yeah, it doesn't work on this. But this is more or less the same functionality as what you've seen before. The advantage of something like Disco is that it's really easy to use, because it corresponds to just a few plugins, so that the functionality limited, but it's extremely fast and very user-friendly. So people that can use a spreadsheet can also use a tool. To come to a conclusion, I hope that, yeah, as I said in the beginning, I felt awkward because I know that some people are doing research on process mining, for which I did not tell very many new things. Perhaps a bit about alignments, but not the things that are in the middle. I hope that you see that this is very different to what people are used to today in practice. People typically look at spreadsheets, they look at meters, they look at graphs and type of things. They never look inside the process. I hope that you also see that this is very different from traditional data mining with decision trees, association rules and all of these types of things. Where you look at patterns. This is about end-to-end processes, trying to understand why are there conformance problems, why are there performance problems. So if you use a typical BI tool and you have a sick, so think of your non-performing process as a sick child, the only thing that you can do is to measure things. You have no clue what the reason is. So process mining can be more seen as X-raying your processes, that you really look inside the process and you can see what the issues are. So if you're interested, for the people that didn't do that, there are many people in the lab that can help you with this. And you can download the software that I just showed you. Try it on your own data sets. There is also a Coursera course running at this point in time, and I think also some people in the room are following this. I just checked, there are more than 36, so in this week I think again we became 2,000 people or something like that. So as I say, if you're interested in this, you cannot make the exams, etc. anymore, but you can still look at the slides and the movies and all kinds of other stuff. Okay, thank you very much.
Questions, remarks, comments?
Do you have situations where you have to align more than two sequences? Then if yes, then how many?
We have been doing, in this Philips project, we have been doing trace alignment, where we would look at multiple traces, but that was without a model. Yeah, that's the classical sequence alignment things we did there. Here it is different from the typical multiple sequence alignment, because we have a model that has potentially infinite many behavior. So we are not trying to match one trace with another trace, we are trying to match a model with potentially infinitely many paths and trying to find the best path. So the typical, let's say, trace or sequence alignment type of techniques we cannot apply in this setting, or we need to change the problem. However, we are very interested in the problem to do multiple, to align multiple sequences at the same time with one model, for the following reason. If we see deviations, and there are many deviations that have the same costs, and there may be 3 explanations for exactly the same problem, then we have the feeling that we can learn from other deviations which deviations are more likely. And it's not something that we at this point in time ourselves are working on, but the security group in Eindhoven is adding probabilities to alignments based on what happened to other ones. But it's more like a heuristic type of approach rather than anything that is proven to be optimal.
You said while searching for alignment, you're exploring this whole space of all possible alignments, and as it's too big, you try to avoid those which are not leading to the short spot itself.
Yeah.
And how do you do it? How can you know a priori that some step is not leading to the end of progress?
So the way that I presented was a bit misleading, because I showed you the reachability graph, the full graph, and then started look for the shortest path. That's of course not how we do it, because our search space is infinite, right? So that's not the way that we can do it, but it's just to visualize it. So we build this on the fly, right? We start from a state, etc., etc. So the reason why we can prune all kinds of paths is that we use the so-called marking equation. So if you have a battery net, and I can just explain the idea now to you, you can make a matrix where you can, for the rows, they correspond to places, the transitions correspond to, the columns correspond to transitions. Then if there is a 1 in such a row and a column in a cell, that means that transition produces a token for that place. If it says -1, it means the transition consumes a token for that place. So that's the matrix that we look at. And then you solve a system of, you know your initial marking, you can represent that as a vector, a place vector, and you know your target marking, you can also represent that as a vector. And then you can write down a system of inequations that tell you which property should hold to reach the final mark. Yeah? So then that representation is being used. Yeah, I realize it's technical, but it is also technical. But it helps. And so these conditions that I just described to you, they are necessary conditions, but they are not sufficient conditions. They are necessary conditions, but because they are necessary, they help you to throw away all kinds of paths that will never lead to the end anymore. Yeah, that's the basic idea. I could sketch it in more detail, but I think the rest is already lost.
Which type of battery nets the toolset PROM is based on?
So the most of the things are based on ordinary battery nets. If you look in PROM, you also have classes of battery nets with resets, battery net inhibitors. You also have so-called data battery nets. So these are battery nets with guards on the transitions that may depend on variables. However, the techniques that you can apply to these different models, so the more powerful your models become, the fewer techniques you can apply them. So for example, so a typical approach, for example, if we look at battery nets with data, what we first do is we learn the control flow, then we do the replay, then we analyze the guards and the variables, etc., and the data flow, and then we add that to the control flow model. And then we get the battery net with data. Such a battery net with data can also again be used for creating alignments. And so what I said about alignments also holds for battery nets with data, with time, etc.
Can I ask a question? Well, thank you for the lecture. And I have a problem. I have a very huge event log.
Yeah.
It consists of several dozens of business processes. It's a banking sphere.
Yeah.
So can I use PROM for discovering this individual business processes? And events can repeat in each other business process, and they're not unique at all. But
yeah.
I have several patterns that can make an idea of what is the actual business process. There are about 20 processes in this event log.
So if you look at, let's say, scalability, that's one place. Well, what you see is that that's exactly things where you're working on, also in the context of distributed process mining. If you look at inductive miner that I was just showing, that's not the optimal implementation that we have yet, but one single pass through the event log is sufficient. So it's just linear in the size of the log. That doesn't get better than that. Yeah? So that's a simple problem. If you look at alignment, where I was just talking about the marking equation, that is a terrible problem. Yeah? So some things you can do, other things you know that, yeah, that there are certain bounds. So that's the performance related question. Then if you look at the, I think what you are referring to is a bit what we call the correlation problem. So there are two types of correlation problems. There is the correlation problem that you see events and you know the activity that took place, but you cannot correlate it to a particular process instance. That's one problem. The other problem is that you know the process instance. For example, if you get the results of text mining, you know that this had to do with a certain problem, but somebody wrote then some text. So how do you classify that text into an activity description? And so you have these two types of problems. I think your problem falls into the first category. And yeah, that's difficult. Yeah. So one of the things that we try to do in such a situation is that we look at the context of such an event to see whether there are distinguishing things around it that help to localize it at a particular point. There is a group in Lissabon that is doing expectation maximization types of approaches. To, if you have no clue what the case IDs are, to start guessing them. And so there are people have thought about this problem, but of course it's very inconclusive, because you basically ask the technique to start guessing where something may belong, and that's yeah. It's a bit similar to text mining. People that work in text mining are happy if they are 30% accurate or something like that.
Like distances.
Here it's tricky.
Yeah, thank you.
So probably that's it. Thanks.
Thank you.
Thank you very
Yeah.
much once again.